I'll start recording. So if you have to leave at 11, I'll just post this up. We won't go much past, but um, it'll be up on the chemistry playlist in Google Classroom.
Okay.
Okay, let's see.
It's
Calculator.
a 0.24.
0.24 atmospheres. Thank you. Okay, so there's the initial pressure. So we're on to E. The N-butane reacts until equilibrium has been established. Calculate the total pressure in the container at equilibrium. So looking back, they also told us that Kc equals 25. So we're going to have to go down and do a little ice table. So I've got, which one was it? N-butane, the iso, butane, ICE. They said that they initially charged it with 0.24 atmospheres. Oh, except they're using Kc, which is concentration. So I probably shouldn't use atmospheres, right? Atmospheres would be if it was Kp. So how do I figure out the concentration of the gas really easily? What's the definition of concentration?
Um, like it's moles, like
Yeah.
moles per liter.
Yeah, so they told us that this had 0.01 moles and it had a volume of 1 liter. So the concentration is 0.01 per 1. So I'm just going to use 0.010 moles or mole per liter as the concentration. And I started with none of this. Okay, I lost X and I gained X. So this is 0.010 minus X, and this is just X. And then I can set it up so I have products over reactants equals, and they said the Kc value was 2.5. So then I solve. So you guys could solve this one algebraically. You guys okay if I flip that up? So I get 2.5 times 0.010 minus x. I have to distribute x equals 0.025 minus 2.5x. So I've just distributed the 2.5 in there. And then I'm going to add 2.5x to the other side. So I get 3.5x equals 0.025. And then divide by 3.5. You get x equals, Vincent can, oh, I've got a calculator now. 0.025 divided by 3.5. 0.00714. Okay. And it wants us to calculate the equilibrium concentration of, oh, it says calculate the total pressure in the container at equilibrium.
Which
Okay,
means we're gonna have to calculate
which means we're going to have to
the
calculate. So let's get these first. So this would be 0.010 minus 0.00714. So this would be 0.00286 and 0.00714.
wait.
Oh yeah.
Wouldn't the yeah, because this is concentration, not pressure.
Yeah, you're right. You're right. Hey, and what's true about the moles?
They're the same. The pressure's not going to change,
Yeah,
ain't
you're
it?
right. You're right. So the pressure, as long as the temperature hasn't changed, then which it hasn't, then okay, here you go. The pressure is the same. Pressure remains 0.24 atmospheres. Very good. So, and I think we, yeah, I should have probably
Okay.
looked a little closer.
I need to go.
Okay. Says so. Okay, so we've got it. Let's hope that we did all that work for something. It says number two. And justifying the answer would just be it's a 1-to-1 gas ratio. Question two says calculate the molar concentration of each species at equilibrium. Okay, so we just did that. So this would be moles per liter and moles per liter. So good thing we did it anyways. And then III says if the volume of the system is reduced to half of its original volume, what will be the new concentration of N-butane after equilibrium has been reestablished at 25? Justify your answer. So by reducing the volume, I don't think we're gonna have pressure and volume shouldn't have any effect, because what will cutting the volume do to in half, like basically making it smaller, what will that do to the pressure? If you make something half as big, what happens to the pressure inside?
Should double.
Doubles.
Yeah.
The pressure will double, and here's where you have to remember. So Le Chatelier's principle says when you squeeze gases, if there's a difference in moles before and after, then a new equilibrium will be established. In a 1-to-1 case, then the change in pressure has no impact on the equilibrium status. So in this case, it doesn't. Now, in other gas reactions where, say, you have more gas on the product side, then squeezing that gas together by increasing the pressure will drive the reaction backwards. Or if you have more moles of gas on the reactant side, squeezing the container will drive the reaction to the product side. But in this case, pressure will double, okay, but no change in equilibrium.
All right, I gotta head out.
All right, see you later. No change in equilibrium because, again, it's a 1-to-1 gas ratio. Okay, so suppose that in another experiment, a 0.010 mole sample of pure isobutane is placed in evacuated 1 liter rigid container and allowed to come to equilibrium. Calculate the molar concentration of each species after equilibrium has been established. So I think this is the exact same question, except instead of butane, you're putting isobutane in. So do you guys, I think I know the answer to this one. You start with 0.010 moles of isobutane. What's going to happen to it?
It's gonna go to the same equal.
It's going to go to the same equilibrium. And like I know, okay, and that is correct, but I just want to just show you because it's kind of interesting. So N to iso, and this time if we just do it, and we'll just prove that it comes out the same, 0.010 0 minus x, gaining x, 0.010 minus x, and this time I do products minus reactants, or products over reactants, 0.010 minus x over x equals 2.5. So I multiply the x up. I add x. This side I get 0.010 equals 3.5x. I divide by 3.5. I divide by 3.5. I get 0.010 divided by 3.5. I get x equals 0.00285, and that is moles per liter, which, if you guys go look up, 0.285 or 286, so I rounded wrong, so 285 actually should have been 286. That represents x, which it turns out x and x, or x and this quantity, were both the same. So it comes out exactly the same. I would have added one more question to this. What would a chemist have to do to this reaction vessel to shift the reaction to a new equilibrium state? So can you guys, the people who are still on, what would a chemist have to do to shift the reaction equilibrium in this case?
Well, to which side?
Change temperature.
Change the temperature. So all you would have to change the temperature. So it's important to know that this capital K, right, KC or KP or just capital K, these are all temperature dependent. Okay, now they're constant. They're constant for every reaction at a given temperature. So this up above, the whole thing was done at 25 degrees Celsius. So in that case, K is always the same. It's always 2.5. But in the event that they change the temperature, either heating or cooling, then that would change the value of K. And again, these K values, they're experimentally determined by chemists. So the chemist studying the reaction for the first time, they set up this experiment and they measure the K value. That's what we measured when we were doing the iron thiocyanate, the orangish blood red kind of color solution. We were trying to figure out what K was. Okay, let's say you did change the temperature. What would you need to know about the chemical equation to determine which way equilibrium shifts? What would you need to know about the chemical equation to determine how a change in temperature will impact the equilibrium?
You're gonna need to know the stoichiometry.
Stoichiometry, not quite. So in temperature changes and thinking Le Chatelier's principle, you guys remember, like, what if we had known this one? Oops. N-butane goes to isobutane, and let's say it was like this. Is if N-butane changed to isobutane and it releases a little bit of energy, then what kind of a reaction is that? Endo or exothermic? Exothermic. So in an exothermic reaction, let's say the chemist went to heat up the reaction vessel. Which way would that shift equilibrium?
Back to the reactants.
It would shift it to the reactant side, correct. So, and cooling it down would be the removal of energy. It would shift it this way. And it would be vice versa if it was endothermic, okay? The other thing to note would be why do you think that this reaction is neither very endothermic or exothermic? It's basically isothermic. Why is this reaction not really endothermic or exothermic? Can you guys look at these structures?
Because it doesn't mind being either molecule, so it just kind of evens out.
And when it changes between molecules, do any of the bonds significantly change?
No.
No. And if you look, I have, I think I have, you guys, if you count them up top, I have 1, 2, 3 versus 1, 2, 3. I still have 3 carbon-carbon bonds, right? So I have the same number of carbon-carbon bonds and the same number of carbon-hydrogen bonds. So this one is not going to be a huge change in energy. Okay, so this one, I would say temperature has very little effect on this reaction, and pressure has no effect. So this one is purely dependent on the temperature or on the, I guess, the intermolecular forces and how these bonds are rearranging. So, okay, I beat this one to death. Are you guys okay solving? This would be, I think, as complicated of an equilibrium question that they would put on there. You guys noticed that I could solve it with linear equations?
Yeah.
Again, I would be prepared. I would be prepared with Desmos or some graphing calculator, or Vincent, you're well off. I would be prepared for a quadratic, but I highly doubt that they would put a quadratic on the test. So, okay. So let's do this. I'm gonna wrap up. If you guys have any questions, now we're kind of in crunch time, so you guys got to email me right away if there's any problems with your technology or anything that's not functional for your test. Otherwise, I will see you guys Wednesday, and I'll be on from 9:30 to 11. And I recommend studying a couple hours each day this week. And if you have any questions or you want to talk through anything, Wednesday will just be office hours. Try and think. Anything else? Has anyone, Keaton, have you talked to Tyler recently?
Yeah,
Hello.
he's in the call.
I'm right here.
Tyler, you came in later. Sorry.
Yeah,
I didn't
I missed the alarm.
That's okay. Tyler, are you ready to go for Thursday?
Pretty much, yeah.
Okay. And then just making sure 10:30 a.m. is when you can sign in. And they will send you information about how to sign in and give you your ticket ID and all that stuff. They should send you an email tomorrow. Okay.
Okay.
Well then, hey, you guys, if you have not tried the practice test, if you have not tried the little demo, please today go right now, try the demo, make sure you can upload images or upload files, practice using it and get used to it, and then I'll see you guys Wednesday. And that's like ultimate last minute drop dead, because I probably on Thursday will just send remind, but I won't be on a video call until after the test is over. So anyways, Wednesday is kind of our last chance to get anything clarified, and then you guys will take it Thursday. So I'm excited. You guys will do really well. Okay, I'll see you guys Wednesday, unless there's any more questions.
All right. See you, Mr.
All
Ford.
right, bye guys. Have a good day.
Yeah, you too.